So in last video we have seen above order, and for writing electronic configuration three important rules are considered, that is above order, Pauli's exclusion principle and Hund's law of maximum multiplicity. Now in this video we are going to discuss in detail about Pauli's exclusion principle and Hund's law of maximum multiplicity. Now first of all, what is Pauli's exclusion principle? According to this principle, any two electrons in an atom cannot have identical set of all the four quantum numbers. In a particular atom, any two electrons will have same set of all the four quantum numbers, or maximum two electrons with opposite spin can be accommodated in an orbital. So in a given orbital, maximum two electrons can be added, and these two electrons must have opposite spin, means first electron or one electron spin along the clockwise direction, whereas other electrons spin along the anti-clockwise direction. Meaning of these two statement is same. Any two electrons in an atom cannot have the identical set of all the four quantum numbers, or maximum two electrons with opposite spin can be accommodated in an orbital. Now consider the example of oxygen. Oxygen atomic number 8 and its electronic configuration is 1s2, 2s2, 2px2, 2py1, 2pz1. Now the set of quantum number for each electron we are going to write. So these are the orbitals. This is 1s orbital, this is 2s orbital, and these are the three p orbitals, px, py, pz. Value of magnetic quantum number m for these three orbitals. So these orbitals are, for 1s orbital m is equal to 0, for 2s orbital also m is equal to 0, and for 2px, 2py and 2pz orbitals value of m is -1, 0, +1. Now out of 8 electrons, consider the first electron which is accommodated in 1s orbital, because 1s orbital is having lowest energy according to the above order or above principle, and this is the first electron. For first electron, set of quantum number is, value of n is 1, this is principal quantum number 1. Value of L is 0 because this electron is added in s subshell, and therefore L is equal to 0. Value of m is also equal to 0, and value of s is +½ Now consider the second electron. This is the second electron. For second electron, quantum numbers are n is equal to 1 because it is added in same shell. L is equal to 0, it is added in same subshell. M is equal to 0. This orbital is having same m value, that is 0, but value of spin quantum number is different, that is -½ So first two electrons are having different sets of quantum numbers. Now consider third electron. This is the third electron accommodated in 2s orbital. Now this electron is present in second shell, and therefore n is equal to 2. Now L is equal to 0 because it is in s subshell. Then m is equal to 0. For s subshell, m is equal to always 0, and as this electron spin along the clockwise direction, s is equal to +½ So this is for third electron. Now consider the fourth electron. This is the fourth electron. So n is equal to 2, L is equal to 0, m is equal to 0, but only difference is this electron is spinning along the anti-clockwise direction. Therefore s is equal to -½ Now consider the fifth electron. Now fifth electron will accommodate here in p orbital, that is px orbital, and for px orbital m is equal to -1. So set of quantum number is n is equal to 2 for fifth electron. Why 2? Because principal quantum number is 2. This p orbital present in second shell. L is equal to 1 because it is present in p subshell, and therefore L is equal to 1. m is equal to -1 because it is present in px orbital. For px orbital, m is equal to -1, and as it is spinning clockwise direction, s is equal to +12. So all the 5 electrons are having different sets of quantum numbers. Now consider 6th electron. It is accommodated in 2p or 2py orbital. So for 2p orbital, n is equal to 2, l is equal to 1, m is equal to 0. M is equal to 0 and s is equal to +12 because this is spinning in clockwise direction. Next electron present in 2pz orbital, and for this orbital set of quantum number is n is equal to 2, l is equal to 1, m is equal to +1 and s is equal to +12 again. These 3 electrons are spinning in clockwise direction, therefore they have same s values. Okay, so now consider 8th electron. Now 8th electron again enter in 2px orbital, and therefore set of quantum number is n is equal to 2, l is equal to 1, then m is equal to -1 and now s is equal to -12. So in this way, in oxygen there are 8 electrons and all the 8 electrons have different sets of quantum number. At least one quantum number is different than the others. Now when you consider first 2 electrons, these 3 quantum numbers are same, but 4th quantum number is different. Similarly, when we compare 3rd and 4th electrons, then first 3 quantum numbers are same, but spin quantum number is different. Okay, this is about the Pauli's exclusion principle. Now consider the Hund's rule of maximum multiplicity. According to this Hund's rule of maximum, or this rule, it is applicable for the filling of electrons in degenerate orbitals. Degenerate orbitals means orbitals having equal energy. For example, 3p orbitals have same energy in the absence of magnetic field. 5d orbitals have equal energy in the absence of magnetic field. So this rule is applicable for the filling of p, d, f orbitals. And according to this Hund's law of maximum multiplicity, there is no pairing of electrons unless all the available orbitals of equal energy are singly occupied. Okay, we will take example. Again, you consider the oxygen. Atomic number is 8. It means there are 8 electrons, and one way of writing electronic configuration is 1s2, 2s2, 2px2, 2py2 and 2pz0. So 2 plus 2 4 plus 2 6 plus 2 8. This is one way of writing electron, and this is the box type arrangement. So in 1s orbital there are 2 electrons. This is the first, second, third electron enter in 2s orbital, fourth electron also enter in 2s orbital, because capacity of each electron is 2 electron. According to Pauli's exclusion principle, maximum 2 electrons are accommodated in single orbital with opposite spin. Now consider fifth electron. It is accommodated in 2px orbital. This is fifth. This is sixth. It is accommodated in same electron, same orbital. Then 7th and 8th. So this is one way of writing or filling the orbitals. Now another way is, again this is the configuration: 1s2, 2s2, 2px2, 2py1, 2pz1. So 2 plus 2 4 plus 2 6, 7 and 8. So this is another way of writing electronic configuration for oxygen. So these are the values of magnetic quantum numbers. Now this is the first electron, enter in 1s orbital. This is the second electron, enter in the same orbital. This is the third electron. This is the fourth electron. They have opposite spin. Now fifth electron, this is sixth electron, seventh electron. You can see here. Now each of the 3 degenerate orbitals, degenerate p orbitals, are singly occupied. So this is the 7th electron. Now after filling or singly filling the p orbitals, next electron paired with the other electron. So here 1s2, 2s2, 2px2, 2py1 and 2pz1, and this is the correct electronic configuration, whereas this is the wrong electronic configuration, because this second electronic configuration fulfills, or as per the Hund's law of maximum multiplicity, there is no pairing unless all the available orbitals of degenerate or equal energy are singly occupied. Okay, so this is the correct, second configuration is the correct configuration for oxygen, that is 1s2, 2s2, 2px2, 2py1, 2pz1. Okay, now next we try to write the electronic configuration for some elements. So this is the above order 1s, 2s, 2p, 3s. Already we discussed about this order, how to write this order. For hydrogen, total number of electrons are equal to 1. It is accommodated in 1s orbital and its configuration is 1s1. Now consider the helium. 2 electrons are there. These are accommodated in 1s orbital. So configuration is 1s2. For lithium, 3 electrons are there. So 1s2, because 1s orbital is now completely filled, and third electron enter in 2s orbital, and therefore 1s2, 2s1. Beryllium, there are 4 electrons. First 2 electrons enter in 1s orbital and remaining 2 electrons are accommodated in 2s orbital. So configuration is 1s2, 2s2. Now consider the boron. 5 electrons are there. So 1s2, 2s2 and fifth electron now enter in 2p orbital. So 1s2, 2s2, 2p1. So in this way electronic configuration is written. Now consider most important element, that is iron, atomic number 26. Now how to write electronic configuration? Now first of all write the order of orbitals, ss, ps, ps, then dps, 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 only I am considering d, dps, dps, f dps, f dps, like that. We discussed this at the time of above order. Now number the s orbitals, 1, 2, 3 and 4. Now number the p orbitals. P orbital starts from second shell, so 2 and 3. D orbital starts from third shell, so 3. So these are the orbitals arranged according to increase in energy. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. Now capacity of 1s orbital is 2. So 1s2, capacity of 2s orbital is also 2. Okay, there are 3 p orbitals and capacity of 1 orbital is 2. So 2 3s are 6. So 2p6. So then 3s2, again capacity of p orbital is 6. So 3p6. Then again 4s2. So capacity of s orbital is 2. So up to 4s, how many electrons are there? So 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20. So 20 electrons are filled. Now at iron there are 26 electrons. So 6 electrons are remaining. So these 6 electrons are accommodated in 3d subshell. So 3d6. And this is the electronic configuration of iron. That is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So in this way one can write electronic configuration of any element, complicated element. If you remember above order, Pauli's exclusion principle and Hund's law of maximum multiplicity.